Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
Go above and beyond.
they become very good at what they do, but only
0.1%.
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
With Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on Current Initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Dr. Anne Rajnicek. She's a senior lecturer at University of Aberdeen, part of King's College. We're going to talk about bioelectricity, spinal cord injury, and tissue regeneration. So, Anne, thanks for coming.
Yeah, thanks for the invitation.
If you would, in your own words, tell me about your research. What are you focused on?
Well, I'm interested in a lot of very diverse topics, but the thing that sort of overarches all of them is the role of bioelectricity. And I'm interested in the role of electricity in wound healing, nerve repair, development, tissue regeneration. So it covers a lot of ground, but the thing that's in common behind them is how the body's own electricity, or the ability to apply an electrical field to tissues, can change their behavior.
Yeah. What is most people's understanding of where and how electricity is used in the body? And then I want to ask about, more advanced understanding of it because of your research.
Yeah, it's when I tell people about what I do, a lot of people start to think that I'm interested in the kind of electricity that might come from an overhead power cable, or the electromagnetic fields that might be coming off of that. And that's not anything like what I'm talking about here. My interest is in how the body uses the transport of charged ions from one place to another to create an electrical current. And by maintaining a voltage difference in one part of the body compared to the other across something like a membrane or a layer of skin. And that means that piece of skin is essentially a battery. As the ions move, they move with their charges. And if you maintain a charge difference across a layer of skin, for example, or across a membrane, if you're a cell, then you effectively providing it with a battery. So your skin is a battery.
Yeah, I guess also what cells have voltage gated ion channels and things like that to allow transport of materials in and out of the cell.
So the electrical properties of skin, for example, the battery that I was talking about, they've kind of been understood really well in frog skin. So that's kind of the best way to explain it. So that you have a layer of skin, and that each cell in that piece of skin is tightly joined to its neighbor. So you get this layer that's got a very high resistance. So nothing's passing through it. And then when you get a frog skin, for example, the sodium ions are taken up from the pond water into the animal so they can do work, so they can serve a purpose in the animal. But then they don't leak back out because of this very tight seal across the epithelium of neighboring cells. So what you end up with is a one-way flow of sodium into the animal from the outside to the inside. So the animal is scavenging sodium from its pond water. Now, when you have more sodiums on the inside than on the outside, if you stick an electrode in through that skin, compared to the pond water, there is a positive charge on the inside of that animal because there's more positive sodium ions. If you poke a hole in that skin, then those sodium ions travel out and you get a wound current. So as those sodium ions are traveling out the wound, then you're getting a wound current, because in a biological system, this particular current is defined by the movement of the positive ions. And you will have experienced this electrical field that's resulting from this in your own body. So example, if you bite your cheek, this happens in your cheek cells as well, or the cells of any epithelium in your body. If you bite your cheek by accident and you put your tongue on that wound, you'll feel a little tingle. Now, I don't know if you were like me, but when I was a kid, I had brothers, and sometimes they would play tricks on me, and they would give me, the old square 9-volt batteries, and they would find one in their bedroom and wonder if it was still live or if it was a dead battery. And if you put your tongue, and I'm not encouraging you to do this, but if you put your tongue across both of the leads on that battery, you get a tingle. And that is exactly the kind of tingle you're feeling with your tongue on the side of your cheek when you have a wound in your cheek. So there is a wound-associated electric field with every epithelium in your body. And so my interest is, what's the role of that electric field in the tissue? How does it play a role in wound healing? And how can we harness this electrical properties, natural electric properties, and the cell's natural ability to read these electrical signals? How can we use those to make clinical therapies to fix things like nervous system disorders and wound healing?
What are some of the properties of human skin? Like I'm imagining like a person when they get older, their skin gets thinner, and that would change the electrical properties. Like, what is the typical capacitance of skin in different areas, and the resistance, and what does this tell you?
Well, what we can do is to measure the electric field within various tissues in various places. And pretty much in general, your skin is a weak battery. So you have something like a frog skin is something like 60 millivolts across that epithelium. It will be less than that for example, in the cornea of the eye, it will be about 30 millivolts, but it's still sufficient to cause biological changes in the cells near that piece of tissue. So for example, the electric fields like I'm talking about, that could be in epithelium of the eye or an epithelium of the gut or the lung or the outer layer of your skin, they can be anywhere from 30 to a couple of hundred millivolts per millimeter as an electric field. And if you take the cells from the skin and you put them in a culture dish and you expose them to an electric field of that size, you can see that most times cells will migrate toward the cathode, toward the negative pole of that electric field. And the kind of skin battery and injury potential that I told you exists in wounds in the skin, the center of that wound tends to be a cathode. So what we see in cells in tissue culture dishes corresponds to the direction that cells would need to migrate to fill a gap or fill a wound. And so there is a link between the natural inherent electrical properties of skin and its ability to heal a wound. So you raise an interesting question about aging. So as you age, the electrical properties of your skin reduce. So the skin of older people tends to not heal as well. So for example, you can think of a condition, for example, diabetic ulcers in the foot. They're a big problem. These are wounds that tend not to heal. And one of the big questions is that happening because the electrical properties of the skin are different in diabetic versus non-diabetic skin? And this is something we're interested in studying and have begun to study, but don't have results on yet. Or is it that the cells of diabetic skin are not able to read and respond to the electric field appropriately, so that the electric field can act as the cue to tell the cells how to fill the wound? So normally the center of the wound is a cathode, and the cells would migrate toward the cathode to fill the wound. So the question is, in something like diabetic skin, do the cells just not read that cue? Are they unable to read that cue? And could you put an electric plaster on the skin, for example? If you put an electric bandage on the skin to improve wound healing. And there is evidence that from other groups that is true, that you can artificially enhance the electric field with a battery.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
Yeah, if you put a Band-Aid where the center part of the Band-Aid was positively charged and you put it over a wound, perhaps that would increase the cell-to-cell signaling and get cells to migrate to that area and cover the wound space. Like if you had a large wound, let's say you stitched it up, but you wanted to take it further, you could probably put a covering over it with, electric charge in the right geometry, again, to facilitate wound healing, to direct the cells into the area that's not covered.
Yep, there's considerable evidence actually true. And you raise an interesting point with the stitching things up as well, because there's a really interesting bit of work that was done way back in sort of late 70s, early 80s, looking at fingertip regeneration in children. And there was a study that was done by somebody. They did not go around and amputate fingertips of children, I have to hasten to add. Children quite often get their fingertips slammed indoors. And so it's not an uncommon injury in a very young child. And what happened was this study was done by 2 people called Illingworth and Barker. And when these children came to the hospital, in one group of children, they stitched up the wound in the usual way, making a skin flap to cover the wound. And in the other group of children, what they did was they left the wound open and they covered it up with a sterile dressing. And the idea there was that by stitching the wound up, you're preventing the natural wound-associated electric field that should be associated with that injury. So you've sealed it up and you've prevented that wound injury current from flowing freely. But if you put the wet dressing on it, that still allows the ions to move freely through that injury site. And what they found was that 6 weeks later, the children that had the open but maintained sterility, the open wound, but it was still sterile, they found those children regenerated their fingertips, complete with fingernail, whereas the other children sort of had a truncated stump. And the important thing there's an important caveat, is that has to be very young children, and it can only be above the first joint. So no joint has ever been shown to be regenerated in mammals. So the very tip of the fingertip can regenerate if you leave the electrical conditions correct. And they actually went and measured the injury current, and it was associated with successful regeneration. The higher the current, the better the regeneration. And as again, going back to the aging question, as children aged, the natural electric current reduced. So, and it was associated with less successful finger regeneration.
Has anyone been able to raster over a particular area and map the differences in, voltage, capacitance, whatever it may be, over a piece of skin? Like, let's say I have an old, scar on my arm.
Yes.
Has anyone tried again to raster over the area over normal skin and over the scar and look at the differences? And what does that imply?
Yeah, there's a colleague, Rajnicek, a few years ago, he invented this device called a dermacorder, and it was intended for exactly that purpose. So it was essentially what's called a Kelvin probe. So it was able to scan over a piece of skin non-invasively. So it never had to touch the skin. It would measure, it would come close to, but not touching the skin. And it would map the electrical potential in the area of a wound. And as you scanned over the wound, it confirmed that the center of the wound was indeed a cathode, and that you could get different sizes of current and different sizes of injury potentials depending on the type of wound. And you could measure, I've used this device on myself to scan over a pinprick wound of the kind of, like you would use a lancet, of the kind you would use to get blood for a diabetic person to test their blood sample. You just a pinprick wound, and you'd scan over it, and it got very clear results with that. And he measured in mouse skin, the injury potentials in mouse skin, and found that once the skin healed up, then the injury current disappeared. So as long as your skin was healthy, you wouldn't be able to detect this injury current. But as soon as
Okay.
you cut it, it appears. And the other thing is that's interesting about it is it's the first signal that your skin will receive that there's an injury because it's instantaneous. As soon as you cut your skin, those ions leak out.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
Well, what about, again, for certain wounds, if I have, let's say, a battery Band-Aid, I have a Band-Aid made of 2 parts, one's, highly negative, one's, not as negative, use something to induce a, small current locally across a wound gap. What do you estimate that would do?
Well, it depends on what the injury is that you're trying to repair. And one of the things that's interesting is when people have used these electrical treatments, it's not always that having the cathode in the center is the best thing, depending on the size of the wound. Some of these electrical therapies that have been shown to be beneficial use the positive pole in the center for a while, and then they reverse it after a few days. So it's possible that it's not as clear and straightforward as just making a cathode in the center. But one thing we do know is that whatever the polarity of the electric field, there is something happening to the cells that are participating in that wound healing event. And it's not even just the cells that are migrating in. Some of the work that we've done looks at immune cells. Mm-hmm. And immune cells are really interesting because, as I've said, the cathode is the center of the wound. So some work that I did with a colleague here in Aberdeen, who's an immunologist, we took human immune cells. So we took macrophages. So they're the cells that go in and eat up all the debris and any bacteria that might be in the wound and help to clean up the wound. And we were surprised to find that instead of these cells migrating toward the cathode, which would have been in the center of the wound, they migrated toward the anode, which would be toward the edges of the wound. And this surprised us. But one thing that was very clear-cut was that these macrophages were more efficient at eating up debris and basically doing their job once they'd had a 1-hour pulse of the electric stimulation. So this was all in tissue culture. So you'd give them the 1-hour electric field that was of the size that you would expect to find in a natural human wound. And then you gave them something like plastic beads or bacteria to try to ingest, which is the job of macrophages. And they were much more efficient at it when they had the 1-hour pulse of the electric field. But the cells that are monocytes, from which the macrophages are derived. So monocytes are circulating immune cells, and they are attracted to the injury site. And when we looked at how monocytes responded in vitro, we found that the monocytes actually did respond to the cathode. So what we think is that the monocytes are the first responders, as it were. So they migrate to the center of the wound, which is the cathode. And then as the monocytes mature, they migrate to the edges of the wound, which are the anode, and they are much better able to digest the debris and the cellular remains and tidy up the wound edges to help promote wound healing. Epithelial cells, which do migrate toward the cathode, migrate toward the center of the wound throughout the healing process. So there's sort of a two-pronged benefit of having the electric field present in the wound.
What about cancer? Has anyone looked at a patch of skin, affected by melanoma, or there's a tumor beneath the surface?
Yes.
And,
So
has anyone looked at tumors, et cetera?
Yeah. One of the things that the dermacorder was used for was to look at skin that had potential cancers, and it was able to detect them. And the interesting thing about cancer cells is that we know they have a different electrobiology. So they have different electrical properties than non-cancer cells. So cancer cells, a depolarized membrane potential. So instead of having this ion difference across an epithelial layer, like I described, if the ion difference is just across the single cell membrane, if you have a depolarized cell, that condition tends to favor cell proliferation. So it would encourage cancer cells to divide, for example. But if you have a hyperpolarized cell, it can also change the way that a cell its fate is changed in terms of differentiation. So we do know that there are specific ion channels that are involved in sort of changing a cell from non-tumor to tumor. And in fact, changes in membrane potential appear to be related to that tumor cell's ability to migrate and become metastatic and migrate around the body. So there is a very clear link between membrane potential and the cancer potential of a cell and its ability to migrate. So that means that membrane potential is maintained by voltage-gated ion channels and other ion transport properties of the membrane, that these might be very good targets to start thinking about, and people are thinking about, as ways to treat cancer in a new way.
Yeah, no, that's very interesting. So what is some of the experimentation that you're doing to try to figure out the importance and the geometry, et cetera, of these fields?
So some of the things that we've been looking at are looking at like the experiments that I've told you about. So I'm pursuing some more work with immune cells right now. In fact, I came from the lab today with some students who are starting to look at that. And the big question is, how do cells, not just immune cells, but all cells, how do they read an electric field? And so the students are trying to figure out what the way is, looking at membrane potential, for example. Is there a gradient in the membrane potential of the cells that are exposed to an electric field? What other properties of the cells are different when they're in the field and not in the field? The big question really is how these cells are reading the fields, because if you add a drug to a cell, that drug can bind to a receptor. There's no electric receptor. It doesn't have that same interaction with the cell. And this is something that's been studied for a very long time, and we still don't have a very clear answer to. And not all cells read an electrical field in the same way. So our experiments right now are basically looking at the properties of the cells that are in the fields and not in the fields, looking at things like membrane potential, for example. We're also looking at the role of applied electric fields in tissue regeneration on a smaller scale, for example, in regenerating flatworms. What are the electrical properties of the worms? Because in order to regenerate, they have a very large proportion of their body that's composed of stem cells. So does the application of the electric field in that situation, or the natural electric field that exists in the worm, does it help cells to find the address to regenerate the appropriate tissue? So if they needed to regenerate a new head, what are the electrical properties that would encourage that stem cell population to become head, as opposed to the electrical properties that would cause that stem cell to become tail, appropriate cells? So we're interested in tissue regeneration.
I don't know if you probably know about Michael Levin at Tufts University.
Yeah, I know
that kind of stuff.
Mike's a close colleague. Yep. We kind of very close overlapping research interests. I also have a particular interest in spinal cord repair and spinal cord regeneration, and how applied electric fields can encourage cells to grow through an injury site, not just in the spinal cord, but also, for example, in stroke. So any central nervous system injury is a complicated situation. And our brains and spinal cords are very, very poor at spontaneous regeneration, partly because they form a scar that attempts to isolate the injury site from the rest of the region, and partly because within that scar tissue is a central space, a central gap. And so what the cells have to do, if the axons want to regrow across that injury site and reconnect functionally on the other side of the injury, they need to get through that somehow. So they must have to grow either through or around that injury site. But there are molecules in that injury site that prevent axons from growing. And as soon as axons get to that region and detect those molecules, they stop growth. So the idea is, can we use an electric field to stimulate the growth of the axons sufficiently that they can ignore those stop growth signals and just continue to grow straight through? And a colleague of mine, when I was doing my PhD in the USA from Purdue, Richard Borgens, he used an electric field applied across human spinal cord injuries and found that he could improve sensory function in those human patients. But for a variety of reasons, he discontinued those studies. But one of the things that needs to be worked on in that respect is defining the electric field that is effective. What kind of electric field do we need to apply? Is it better to have an electric field that oscillates in two directions so that you get axons being attracted toward the cathode and toward both the head and the tail? And the answer to that has to be yes, because we have to restore function of the sensation as well as motor function. And that means that nerves have to grow in both directions to reconnect. And so what he was looking at was using an oscillating field where it was 20 or 30 minutes in one polarity and then 20 or 30 minutes of another polarity with electrodes implanted on the surface of the spinal cord. But what we don't know is if he had the conditions right. Was the field strength appropriate? Was the duration of the oscillation appropriate? And we also know that implanting metal electrodes into the central nervous system is not always the best idea because they can there are inherent problems with metallic electrodes implanted into the body. So you get pH changes, free radical formation, temperature increases, and local tissue necrosis right near the very tips of the electrodes. So we have to find something that is better than a metallic electrode. So I've been working with a colleague who's been designing non-metallic electrodes, and we found that we can grow nerves on those, and we can direct cells, either directing their speed or their direction of growth by changing the type of electrode material that we're using. So we're growing them directly on a material that is electrically conductive and without even connecting it to the electrical circuit directly. So we can indirectly cause the electric field to develop within that piece of material, and we can control the way the cells grow within that material, which is an improvement over metallic electrodes. It doesn't have any of those consequences. So we're
what about magnetic induction? Could that be used so it's non-invasive?
Yes.
Use of exterior magnets, let's say, to target a certain tissue and induce electric fields to simulate healing in a session?
Yes, you possibly could. Now, that's a bit outside of my expertise because I'm looking specifically at DC electric fields rather than any oscillating fields that you might get from a magnetic field. So it's a little bit outside of what I do. I'm trying to look at the way the cell would normally make these wound currents, these injury currents that I was talking about. They're direct current electric fields. This is an ion moving from one place to another, exactly as you would have in a DC current with electrons flowing through a wire. But in the body's using sodium and chloride and moving those around instead of the electrons themselves. So, this is something that's got a really big future ahead of it, I think, because people are starting to think about bioelectricity in novel and innovative ways. So there was a new thing that was a buzzword a few years ago, electroceuticals, where you could create little tiny electric devices that could stimulate nerves, and then you could get some sort of clinical outcome from that. And that's true, and that's beneficial. I like to have a wider view of the idea of electroceuticals. I like to think that you could also just be, as we've talked about in cancer, you could modulate the ion transport across cells and tissue layers, and that the body could itself regulate this electrical circumstance by just us affecting ion transport. So it's more than just implanting something in the body. It could be a wider understanding of how electrical signaling is important in cell migration and tissue regeneration, stem cell differentiation, all those sorts of things.
I wonder, something flashed in my head. I wonder if the epithelial to mesenchymal transition in cancer is modulated by electric fields. And, when it breaks through a basement membrane of cells, based on what you're saying, the electric field would change. And I wonder if that would help facilitate EMT, or it could be a cause or a driver of it.
It could be, it's certainly a component, I would say, and as well, because the extracellular environment is what we're talking about here. So what kind of electrical environment are cells residing in, as well as what is their membrane polarization state or depolarization state. So we know that stem cell differentiation is affected by hyperpolarized membrane potential. And we also know that there isn't any such thing, as you've kind of hinted, it's not a uniform electric field. Differences in tissue resistance from one place to another are going to change that. So for example, when we have these little planaria worms and we can measure the voltage gradient from the head to the tail within the animal, and we assume that there's a voltage gradient of, across that worm, but it's not going to be linear. So it might be that the major part of the voltage drop in that worm is in the head and not so much in the tail, and that's the important thing that's going to drive the differentiation state of the stem cells that need to regrow ahead in that region compared to the cells that are growing a tail in the other region. And we already know that there's a difference in the membrane potential of the head versus the tail. So there's probably this sort of two-pronged attack to the electrical environment and how it can contribute to things like differentiation of stem cell fate.
I guess, yeah. I mean, there's still a lot to be known. I'm imagining, again, putting a series of, let's say, magnets or inducing electric current over and around a tumor, oscillating it at some frequency. And I wonder what it would do to the tumor if it would disrupt it. Many ideas, but I guess there's a lot more research needs to be done.
Yeah, one of the other things that has been done, again, by Rich Nicitelli, who was the guy who invented the dermacorder, he has used very high frequency electric fields to ablate tumors. It's quite a radical procedure. He would take, he would pinch the tumor for skin tumors, for example. He would pinch the tumor between two conductive plates, and he would deliver a very high frequency, high voltage discharge, and he could ablate tumors in that way. So it can be used that way, but the kinds of fields that I'm talking about are much, much lower than those that he would have used for that.
So what's the future of your research over the next couple of years? What hypotheses are you hot on the trail of?
Well, again, I think the holy grail for me is finding what the mechanism is for how cells read electric fields. It's probably pretty boring for other people to think about, but I think it's quite fascinating because people have been, we've known about electric fields for a long time. People have used them in some sort of clinical context for as long as people can remember. The Nile catfish was used, and torpedo rays were used by Romans and Greeks and Egyptians for curing things like gout and headache, but nobody knew how they worked. And we still don't know how most of these electrical therapies work because we don't understand well enough how cells read bioelectrical cues. So, there's a growing appreciation for this. When I started my PhD looking at the effects of electric fields on epithelial cell migration and how nerve growth cones, which are the tips of growing nerves, how these properties that are present in embryos, how are they used to make an embryo get its shape? We started trying to publish papers and people would say, this doesn't make any sense to me. And I never understood why people would believe in the membrane potential as a concept, but couldn't understand the idea of a transepithelial potential across skin. To me, that is not a large leap. That's it's a scale thing. It's a voltage difference across space. And people would not understand that this voltage could be used for work in a sensible way, to guide cells to where they need to be, to cause cells to differentiate. But now there's a much better understanding of that. And to a large extent, that's come from improved abilities to read the electrical signals and to manipulate them in very, very more refined ways. So 30 years ago, you would say bioelectricity to people and they would just, they would wave their hand at you, but that is not the case anymore. In fact, there's now a new journal that we've started up to try to bring people together in this community. And the number of papers has been incredible. And I write a little bit in it called Bioelectricity Buzz, which is a blurb at the end where I just try to round up all the bioelectricity hot stuff that's happening, not published in our journal, but published everywhere. And it's so easy to find really exciting stuff that's going on with like the neural brain interface and genetic technologies and an ability to get really fine-tuned probes, fluorescent probes for membrane potential and all kinds of cellular readouts that we could have never imagined years ago. And nanotechnologies, it's really exciting right now.
Oh, I know this will be not exactly within your wheelhouse, but maybe an easy cohort you could get is a group of people that keep their cell phone on them in a certain place, in a pocket, in their bra, wherever it may be, and then look at the condition of the skin where the cell phone sits next to. And maybe that would give you, again, an easy way to get some additional information about bioelectricity, because again, people are voluntarily and unknowingly putting a device next to them that, is emitting some fields and, who knows how it's affecting the skin around them.
Yeah, like you say, that's not quite my area of expertise, but I remember a little while ago looking into this and not looking into it formally, but just reading about it. And there's been a long history of people holding mobile phones right next to their ears, right? There was a supposed link to brain tumors on that side of the head, but I think that's been disproved. And a lot of people keep their phone, you're right, keep their phone in their back pocket or wherever. But I'm not aware of any literature or any claims that there's been any biological consequence of that. I might just be missing it because, like you say, that's not really my exact area.
Well, I mean, since you're in this field, though, what if an object that's emitting an electric field sits in close proximity to skin? I'm not saying tumors or anything like that, but how does it affect the localized skin that it sits next to if it has its own field? It would distort the skin field at least somewhat. So I wonder if it would do something, nothing, but it probably would do something.
Yeah,
I just wonder how we could characterize it.
Yeah, but the resistance of the skin is quite high. So, how much of it would get inside through many layers of lipid and your dead skin cells, which would also be insulating on top. So I don't really know how much of it would penetrate. As far as surface skin tumors, I just don't know. I think you'd probably have to keep it there for a very, very, very long time. I don't know the details about what the radiation that's emitted from modern phones is. I know it's changing all the time. So I couldn't really comment on that in any intelligent way, I have to say.
Yeah, I'm just saying you have a perspective where you'd be open to looking to see what happens, if anything. So it's just an idea for you. Hopefully someone else will do the experimentation and you can look at it with your point of view and maybe infer something interesting.
Yeah, I mean, I think you're right that a lot of people are unwittingly doing that experiment right now. So we'll watch this space and see what happens. I would think that people would have started reporting things in literature if that had been coming up in clinics, but I just don't know. Can't really say anything about that. I do carry my phone on my body just like everybody else, so we'll see.
Right.
I'll let you know if I see anything.
Maybe you do some secret self-experimentation and look at the skin in the area and see,
Yeah.
Well, very good. What's the best way for people to find out more about your research? How can they contact you or look up your papers and stuff?
Probably through my university webpage at the University of Aberdeen. I have to kind of correct you a little bit. You said I was associated with King's College, and that's not strictly true. I'm at the Institute of Medical Sciences. I'm in the School of Medicine, Medical Sciences, and Nutrition in the Institute of Medical Sciences. King's College is where our admin is done. So that's a different campus.
Oh, no problem. Well, Anne, again, thanks for coming. It's been a really interesting subject, and I appreciate you being here.
Well, thanks for the invitation.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.